Hi everybody, Mr. Skelton here. We are back at it, lesson 2 in unit 8, and today we're going to focus our attention on functions and get into a little bit more detail than what we did in lesson 1. If you remember from lesson 1, our focus was basically just on the graphs, some different graphs. We had linear, so y equals mx plus b, right? We had quadratics, we had absolute value, and we talked about all the shifts, right? We did some examples of x minus h squared plus k, where you have your a value, which stretches and shrinks. You have your h and k, which could be your vertex, or how you shift things. And so we talked about some specific functions, and we graph them. And today we're going to talk a little bit more about what a function is. And you did a lot of this in Algebra 1, but just a reminder of what functions are and how we can use them. And then we're going to get into piecewise functions. That'll be the new thing for you. Towards the end, that'll be brand new for you. So let's just jump right into it. These first couple slides, I'm going to try to go as quick as I can, but since it is review, but I still want to make sure you understand our function stuff. So parts of a function. You have the domain, the range, and the rule. A good analogy for a function, and I might have used this before, is you take your x values, you plug them into said function, and something happens during the function where you plug the x in, and you get your y value out. Okay? That's the basic idea of a function. We'll talk about some of the rules here in a second in terms of what functions need to be. But let's talk about it. Domain. Domain is your x values. Domains are your inputs. Domains are your independent values. Okay? All four of these, domain, x, inputs, independence, they all mean the same thing. So it's four different ways to identify your x values. Okay? Your range are your y values. Okay? X and y for domain and range. They're your outputs, and they're your dependent. Right? Your range depends upon the x values, the independent values that you plug into the function. Your range, your y, your outputs, your dependent values are your all your y values. Okay. Your rules are represented in a variety of ways. They could be a linear function. They could be quadratic functions. They could be cubic functions. They could be any type of function rule that we've been covering in the past. They could be absolute value. Okay. All of those are rules that you could plug things into. Okay. So just a quick example. We could do something like this. Y equals x plus 7. That is a linear rule. That is a linear rule. And let's say x equals 6. Okay, what would happen? Well, we'd go y equals, we plug in the 6 for the x, 6 plus 7, and we get y equals 13. Okay, so our input, or our x value, or our domain, or our independent value is a 6. We plug it into the function rule, which is y x plus 7, which is adding 7, and we get 13, or our output as a result. Okay? Basics of a function. Now, the overlying rule or definition of a function is it has to be 1 to 1. And what I mean by that is every input has exactly one output. And it can't break that rule. Okay, there's only one output for every input, and we'll talk more about that here in a second. So let's turn the page. Okay. So something called function notation, and we've talked about this already in class. I kind of gave you this example just 2 seconds ago of y equals x plus 7. If we wanted to put that in function notation, you'll see something that looks like this. This right here is what we call function notation. F of x stands for the function when we plug in x is x plus 7. So that's called function notation. It means the exact same thing. So on the previous example that I did, if we said that x was equal to 6, we would write it like this. We want to know what the function is when x is 6 into the function rule of x plus 7, which would be 6 plus 7, and we get 13. So we would interpret that as f of 6 equals 13. The function when x is 6 is 13. That's called function notation. Now I have f of x. Sometimes you'll see g of x, you'll see h of x. Those are the most common ones that you'll see. Whether it's f of x or g of x or h of x, it's just different ways of writing function notation. Okay? And you'll see g of x, h of x, and f of x when we have more than one function taking place. And you'll see that down the road. Okay? Awesome. So let's keep moving here. What makes a function a function? We kind of just talked about that. A function, what makes a function has to be one-to-one. All right? And I'm going to show you some different examples of identifying whether something is a function or not. Sometimes we use mapping diagrams. I'm sure you've seen these before, where you have like a list of your x values and a list of your y values. So for example, like my x values, I'll draw a line here, 1 and 4 and 5. My y values would be like 3 and 5, okay? And they would map, so you'd have some arrows, like 1 maps to 3, 4 maps to 5, and 5 maps back to 3. In other words, you know, if you had an ordered pair, it'd be 1 comma 3, be 4 comma 5, and it would be 5 comma 3. And you have to ask yourself, is this mapping diagram a function, yes or no? And it would be yes. And the reason it's yes is because every x value has exactly one output. Okay? So that would be a function. Sometimes with graphs. Okay, so here's a graph. Here's a linear function. I'm just making something up. And you remember what we used to call the vertical line test? We did this in Algebra 1, where you would run a vertical line across the graph in red. And what you have to make sure and check to see is that there's only one point on the line at a time. This would be an example of yes, it's a function because it passes the vertical line test. I can run my pencil along this graph, and every point has exactly one y value. Every x value has one y value with it. So let me give you some examples of not functions, or something that is not a function, with a mapping diagram. So x, y. Okay. And let's go 6 and 5, and I'll put a 4 and a 2 and a 3. Okay? So this is an example of not a function. So 6 going to 4, 6 also going to 2, and 5 going to 3. Well, you can see if you make an ordered pair, 6, 4, 6, 2, and 5, 3. What's the problem? The problem is 6, the input, has more than one output. It has 4 and it has 2. That is not, it's not one-to-one. 6 is going to 4 and to 2. If you were to graph this, 6, 4, 1, 2, 3, 4, 5, 6, 1, 2, okay, and 6, and then 4, 3, 4, you can see whatever this graph would be. You know, I don't know what it is. I'm just doing something silly here, okay? But if I ran the vertical line test right there, it doesn't pass because you have 2 points on a vertical line, and that would not be an example. Here's another example, just a circle, right? Just a circle. This point here and this point here, they're on a vertical line. That is not a function. Another example, sometimes you see we just got done doing square root functions, and so if you had something like that, that is not a function because it doesn't pass the vertical line test, okay? So some quick and easy ways to remember this, because a lot of students will get confused, like on this one where you have 5 and 1 both going to 3. What's the difference between that, where they both go to 3, and where 6, where 6 is going for 4 and 2? If your x values repeat, it's not a function. It's an easy way to remember it. Okay? But there's some visuals too. All right, let's keep moving on. Piecewise function. So I'm going to give you an example of a piecewise function. This is new for you here. And then I'm going to, we'll do a couple together. And sometimes this can be a little challenging. I'm going to use a pencil here coming up, and I would suggest you have a pencil as well, because I'm going to ask you to do some erasing at first. But a piecewise function is exactly what it sounds like. It's pieces of functions. Notice I have it plural. So it's pieces of different functions. Here's a real world kind of example. We're not going to graph this one, we're going to kind of set it up. The cost at a salad bar of a Pizza Hut. Let's say Pizza Hut has 3 different prices for age groups, okay? So let's say it's 10 cents, and you're going to kind of see how I'm going to write this up. It's 10 cents for all students, all people who are under 10 years old, so children under 10. I'll put a little if in the middle. Okay, so that's one of the 3 different costs for salad bar. The second one is it's $2.50 flat. Okay, it's $2.50. Let me back up here. I put an X here because it's 10 cents times the age. So if you're 1 year old, it's 10 cents. If you're 2 years old, it's 20 cents. If it's 3 years old, all the way up to 10. Okay, so that's why it has an X there. It's $2.50 just flat between the ages of 10 and 65. Okay, so if you're 65 or if you're greater than 10, then you're going to pay $2.50 flat charge. Okay, and then we'll say just a flat $2 if you're older than 65. Okay, so that's kind of what a piecewise function looks like, and you can kind of see it on the bottom. That's another one that's a piecewise function. Now notice in this one I put f of x, so I use function notation. Where this one has y, you will see both. But that's why, or how we can use piecewise functions in a real world situation. We're not going to graph this one, but I just kind of wanted to show you the application of a piecewise function. So let's get down into what you're going to be asked to do, which is graph these. I would definitely use a pencil, and these can be kind of tricky until you get used to them. So we're going to do a couple of them together here. So what I do, this is my method here, is first of all you got to understand the 3 functions that we have. This is really y equals x plus 2, y equals negative x plus 8, and y equals 2. Some students I've seen in the past will go off to the side and write the 3 out just because it looks better to them. They're not used to the piecewise function stuff yet, and so they want to write out the 3 functions that they have to graph. Now, these right here are all the restrictions that are placed upon your graph, and I'll get to that in a second. So here's why we're going to use a pencil. Let's graph y equals x plus 2. All of us should be able to do that. Y-intercept is 2. Our slope is 1, so we'll go up 1 and over 1. Okay, and I have my 2 points, but then I'm going to draw my graph really lightly here. Okay? Awesome. We should all be able to do that, no problem. Now, the piecewise functions, remember, it's pieces of functions. So we don't want this entire line. We just want a specific piece of it. And the specific piece that we want is listed here by the restriction. We only want this part of the graph where the x values are less than 3. So your attention should be on the x-axis. We're going to go 3 units over. And we want to keep the part of the graph, we want the piece of the graph that the x values are less than 3. So take your pencil, go over to x equals 3, and just go up until you hit the graph, right there. Okay? Now, because it is just less than 3, we're going to put an open circle right where the x value would be 3 for this point, right? This point looks somewhere close to like 3 comma 4. I know that's not exact, but it's somewhere in that range. We want this function to be graphed only with the x values less than 3. So where are the x values less than 3? To the left of 3. So we want to keep everything right here and erase everything that's above or greater than 3. We don't want that part of the graph. So that's how we would graph this first function with x is less than 3. And that should make sense. This counts because your x value would be 2, x value is 1, x value is 0, negative 1, negative 2, negative 3, etc. all the way down. Make sure your arrows are on your graph. Okay? Second equation, 8, 1, 2, 3, 4, 5, 6, 7, 8. Oh, I've got to make my graph a little bigger. Okay? And my slope is negative 1, so down 1 over 1. Get this y out of the way. All right, and again, I'm going to draw pretty lightly here. All right? Now, this isn't going to be perfect. So there's my line. But now, again, I don't want that entire line. I need to just keep the parts that are between. So basically less than x equals 6, but greater than 3. So if you want to make this a compound inequality, you can. Less than 6, but greater than or equal to 3. So that's the part of the graph that I just drew that I want. 6, 4, 5, 6. So I go to 6, okay? It does not have a line underneath it, so I'm going to go open circle. And x has to be greater than or equal to 3, so 1, 2, 3. I go up, and I fill in the circle. Now, if, again, my graph's not perfect. If you get to the point where you're on the same point as the other graph, and this one's filled in, then you need to fill in the circle. A filled-in circle always trumps an open circle. Now, I just want the part of the graph that's between 6 and 3, which is this part right here, so everything else gets erased. Okay? So right now I have this graph, this part of the graph, and then between 3 and 6 right there. Okay? Now the last one is just y equals 2. Remember, y equals, anytime you have like y equals a number, that's going to be a horizontal line. And anytime you have x equals a number, which we're not going to have in this case, but just for review purposes, x equal numbers is always a vertical line. So y equals 2 looks something like this. Horizontal line through y. Now again, we don't want that whole line, we just want pieces of it. What piece do we want? We want the graph where the x values are greater than or equal to 6. So 1, 2, 3, 4, 5, 6, go up to the graph. It's a filled-in circle. X values greater than 6 would be 7, 8, 9. So we just want this part right here, and we will erase everything else that we don't want. And that is a graph of a piecewise function. Okay? Now some of you won't need to graph the whole line and do all the erasing like I did. You'll get used to it, and you might be able to just put the stuff on the graph without doing what I did. I'm kind of taking the longer approach just so you can see that all it is graphing, in this one, linear equations, which you know how to do, and then just erasing the parts that you don't want based on the restrictions given. Okay, flip it over on the back. Let's do one more together here. I know I don't have a slide, but let's just try one. So let's write f of x equals, I have x squared if x is less than 2. We'll do a 6 if x is between 1 and 2. So we'll say x is greater than 1 but less than or equal to 2. And we'll write, do something like this. Let's go 5 minus x if x is between 6 and 2. Okay? So there's our piecewise function. You have to graph that. Go ahead and hit pause and try. Okay, so the first one, we basically have y equals x squared, we have y equals 6, and we have y equals 5 minus x. I'm going to switch that around because I know it's linear, right? So I can write it in slope-intercept form, and we need to graph those. So y equals x squared. If you need to make a t-chart, you can. I'm just going to make a rough sketch of it right now. Just for speed's sake, you should make this accurate, all right? What's our restriction? Where x is less than 2. Well, here's your x-axis. Remember, this is your x-axis here. 1, 2. So we want to keep the parts of this graph where it's less than 2. So we'd go over to 2, go up till you hit the graph, open circle there. Less than 2 would be to the left. So we want to keep everything of this graph to the left of that circle, which means I would erase that. Okay? Y equals 6. 1, 2, 3, 4, 5, 6. This is my y-axis, the horizontal line. I'm going to draw it real light. What do I want to keep? I want to keep between 1 and 2. But at 2, got to be a filled-in circle. So I go up, filled-in circle here. 1 would be open circle at 1, and I want to keep the parts right in between it. So I just want to keep this part of the graph right there, and I can erase everything else. All right, and then our last one is negative x plus 5. So 1, 2, 3, 4, 5. Okay, and then I'm going to go down 1 and to the right 1. All right, and draw my line. Real light. And then I want between 6 and 2. So 2, 3, 4, 5, 6. And it's going to be a closed circle there at 6 and an open circle at 2. And again, I don't know if that's right on top of each other or not. That's okay because I'm just kind of doing an example here. and I want it between, so I want to keep just this part right here, and I would erase the rest. And again, pencil's nice because you can erase, and I know again it's not perfect, but there's another example of a piecewise function right there. All right? We will do plenty of these so you can get some good practice at them, but again, this lesson is really focusing on really two things, just what the basic idea of what a function is, and then the new stuff, which is the piecewise function. Okay? As always, if you have questions, look forward to helping you out in class. Take care.